Hi, my name is Genesis Monroy Rivera. My student ID is 132567. I am a student at the Polytechnic University of Puerto Rico. My course science is 1441, section 8. In this video, I will present laboratory 8, exploring RLC circuit analysis and applications. This experiment focuses on how a series RLC circuit behaves under AC conditions when the frequency changes. The goal is to measure the phase angle between voltage and current using an oscilloscope and to identify when the circuit behaves as inductive, capacitive, or at resonance. In a series RLC circuit, the resistors, inductor, and capacitor together create an impedance that depends on frequency. Because of that, the relationship between voltage and current change with frequency. My hypothesis is that the phase angle becomes positive in inductive regions, negative in capacitive regions, and approaches zero at resonance. Objectives. The objectives were to assemble and analyze a series RLC circuit, measure voltage and current signals using an oscilloscope, determine the phase angle, calculate inductive and capacitive reactance, identify inductive, capacitive, and resonant behavior, compare experimental results with theoretical values, and verify the resonance frequency. To support the experiment, I used the reactance formulas for the inductor and capacitor and the phase angle relationship for a series RLC circuit. I also calculate experimental phase angle using oscilloscope-based measurements and then computed percent error by comparing experimental and theoretical values. For the equipment, I used the Spotec Labrador oscilloscope. I use the Spotec Labrador oscilloscope, a signal generator, a resistor of 1000 ohms, and inductor of 100 millimeters, a capacitor of 0.1 microfarad, a breadboard, connecting wires, and a computer with the software interface. I connect the resistor, inductor, and capacitor in series on the breadboard. Then I connect the circuit to the signal generator. Next, I connected the oscilloscope channels to observe the signals needed to compare voltage and current behavior. I adjust the frequency to specific values: 1 kHz, 1.7 kHz, 1.592 kHz, and 3 kHz. For each frequency, I observe the voltage versus time waveforms. Then I use Lissajous figures to measure the phase relationship. I record time delay and intercept values as needed, organize everything into tables 1 through 6, and perform calculation for reactance, phase angle, resonance, frequency, and percent error. Now I will show my recorded result for each frequency. After analyzing waveforms, I also measured the phase angle using Lissajous figures, which is another oscilloscope method. In this method, the shapes and intercept relationships help estimate the phase between the signals. This figure corresponds to the inductive condition and supports a positive phase relationship. This figure corresponds to the capacitive condition and supports a negative phase relationship. This figure corresponds to the capacitive condition and supports a negative phase relationship. These figures correspond to the resonance condition where inductive and capacitive effects balance. At resonance, the phase angle should be approximately zero. Here are example calculations for inductive reactance, capacitive reactance, and the theoretical phase angle. I also calculate the experimental phase angle from oscilloscope measurements and then computed percent error by comparing experimental and theoretical values. In this experiment, the main instruments were the oscilloscope and signal generator. The oscilloscope introduced uncertainty related to time resolution, voltage sensitive, and interpretation of waveforms, which affects phase measurement precision. I calculate reactance, phase angle, resonant frequency, and percent error. Both systematic and random errors were present. Systematic errors include calibration and component tolerance, while random errors come from reading uncertainty and signal noise. Overall, the experiment showed good accuracy and acceptable precision, especially in the capacitive region. These results matter because they demonstrate how frequency changes circuits behavior, which is important in applications like filters, radio receivers, communication systems, and signal processing. In conclusion, a series RLC circuit was successfully assembled and analyzed. The phase angle between voltage and current was measured under inductive, capacitive, and resonant conditions. The results confirm that the phase angle is positive in inductive behavior, negative in capacitive behavior, and approximately zero at resonance. The resonant frequency was determined and compared with the theoretical values showing reasonable agreement. Despite minor experimental errors, the objectives were achieved. This lab reinforced the relationship between frequency impedance and phase angle in AC circuits.